Last time we were working with some induction, so I want to just keep on working on the problems on worksheet 14. So we were looking at induction and just trying to build out to be more flexible and handle some maybe non-standard cases of induction. So for today, I want to definitely give you guys some time to work on writing your own proofs and get some feedback on that. So I want to go through a couple, we can go through a couple together just to get some ideas about techniques that might help with induction. And then I'm going to have you work on some of the more challenging ones towards the end. So I think that it's good to try some of those. So I don't want to just do some of the easier ones and then leave you out to try on some of the harder ones. But before we get started, are there any questions? Okay.
Quick question, actually.
Yeah.
For the pre-class quiz, there's the last one asking about what was the, I guess, most relevant problem with this proof. Was there more than one, or because it seemed like several things were wrong with it, but I guess we were supposed to pick the most important one.
Let me take a look. Let me open that problem up. And anybody else, if you're thinking of something to do while we're checking this out, you can certainly think about the problem that you're looking at, number 3. We started this last time and we didn't quite finish it. But let me open up the quiz so we can all look at it. So this question here?
Yes.
Okay, so the induction step is not correct. And part of the problem here, so this is actually the problem that we're going to talk about right now. So it's good to talk about this. So one immediate problem looks, so it's okay. The induction hypothesis is fine. All of this is correct. And now they're going to try and show for n values larger than k that the same thing holds. And so part of the problem is, let me draw this up. This is what we want to show. And so we can't assume that it's true from this step over here. So that was one problem. And so if instead you started with this and actually work your way up in this direction, it would be fine. So they just kind of started with the right side and got to the left side where you're supposed to start with the left side and work your way to the right side. I think the algebra is okay. The induction hypothesis was okay. And this last step over here, you don't have to do it that way. So there's nothing wrong necessarily with that. You can do it that way. That's kind of a choice. So out of these, this was kind of the most glaring error, I would say.
Is there a better way to have done the induction hypothesis? Or is it okay just to have said, we're going to assume k is valid and then we're just going to show n to k instead of doing a n minus 1, k minus 1, k plus 1, anything like that?
Yeah, so here you could say, well, let's consider some integer k, which is greater than 2, for example, since we've done the 1 and the 2 case, and say, well, let's assume this holds for some integer k. We can see that's going to be a problem here because we're going to need this to hold for more than one value of k.
Mm-hmm.
And so that's why assuming that it holds for all such values is going to cover cases where, okay, maybe sometimes we just need the kth domino to knock over k plus 1, but sometimes we'll need multiple things to knock over k plus 1. And this is one of these cases where we're going to need more than one domino.
All right. Thank you.
Yep. Any other questions about this one? Okay, let me stop that share. Change this. Okay. Okay, so the base case and we did last time, so that's over here. So the idea here is that we have two special base cases to check, not just one. So these two are defined differently than ones when n is bigger than 2. So we would want to check these differently than when we check n bigger than 2. So the check for n equals 1, n equals 2, we did last time, but are there any questions about that? Okay, so then let's kind of check out this induction step over here. So for the induction step, yeah, we're gonna take integers k that are bigger than or equal to 2 and less than n. And then we're gonna try and show that this would knock over values larger than k. So in other words, this is gonna handle case 3, 4, 5, 6, 7, all the way out. And we're gonna assume this is true for all integers in this range. And we're going to want to prove that for integers larger than k, this same property holds. So I'm hoping at this point you're getting more comfortable kind of with the setup here. These are pretty similar every single time. And then the tricky part is, well, how do we use the induction hypothesis to get the result we're looking for? And that's going to be different in different problems. Okay, so please just let me know if you have any questions. You can chat them in if you prefer that way as well. Okay, so then what we need to do here is we start with this. And then we're going to try and show that. So let's just be sure we're doing this in the right direction. So let's say various ways that we can do this. So I think that students seem to like this, let me plug k plus 1 in and check it out. That's how the book does it. So we can just set a value for n larger than k. Let's pick the very next value. Okay, and then we would have a sub n is defined recursively like this. And now we can use our induction hypothesis. Since, sorry, we're doing it this way, right? I could do it, I could leave it alone with n. I could do it with k plus 1. So if I do it this way, a k plus 1, then the first term, right, would be 2 times a to the k minus a to the k minus 1, right? So this, we need the 2 previous terms to get the k plus 1 term.
Is there times when it's easier to do like either k plus 1 or n minus 1, or like is there certain times when it's going to be easier to do one or the other?
No, I think that you should just be flexible and able to use these different ones, but it's hard for me to say like when you have sequences, you're always going to want to do this, and when you have this problem, you're always going to want to do that. I think that you can use all of these methods in all of these problems, so you might just want to pick one way and do it in all of them. But you do want to be flexible in that other people might do things differently, and so you want to be able to read other people's work as well.
Yeah.
And so that just kind of hits back. Let me just kind of scroll back to this sort of idea here where you could use any one of these methods. And I'll just say the textbook tends to use this one, but there's nothing special about that one, really.
Okay.
Okay, so here we are. We're trying to prove this for the next integer, k plus 1. And so to do that, recursively, we need the ak element and the ak minus 1 element. And we've assumed that this is true, sorry, for all values of k less than n. And our n is k plus 1, so this is less and this is less, right? So we can use the induction hypothesis on both of these terms. And the induction hypothesis tells us that we get this over here. So I can replace ak with 2k minus 1. And then I could replace ak minus 1 with 2 times k minus 1 minus 1. So I'm just plugging in k and k minus 1 into our assumption for the inductive hypothesis. And now what we're going to hope is to show that we get this. And maybe one downside of using the k and the k plus 1 that you need to recognize here, that what we're actually looking for would be 2 times k plus 1 minus 1, right? Because we want to show that this holds when n is equal to k minus 1. And at this point, it just becomes algebra. So we've got 4k minus 2 minus the quantity 2k minus 3. And so then the 4k and the 2k give me 2k, and then I've got minus 2 plus 3, I've got 2k plus 1. And then you might look at this and compare it to this and say, this looks like it didn't work, but why is this okay? Right, I've got plus 1 over here. You might think, I should be looking for minus 1.
Because you're plugging in sorry, hold on. Oh yeah, so that we have the 2n minus 1, and then you plug in the n value, which is the k plus 1.
That's right. We're trying to get this expression not at n, right, but when n is k plus 1. So now we can write this as 2 times my n value, which in this case is k plus 1, and then minus the 1, right? So that does equal the expression we had above. And that's what we wanted to show, and now we're good to go. Okay, so we did 1, we did 2, and now we just did every other case. Any questions?
I have a quick question,
Sure.
actually. So you have the quantity 2 times k plus 1 minus 1. Where did the minus 1 come from? I feel like I'm missing something.
We're trying to get this formula over here where n is k plus 1, right? So we're checking this for the k plus 1 term. Okay. So if this is going to work out, then I should get 2 times k plus 1 minus 1. I want to get when I replace n with k plus 1. And so that's why we wanted the -1 over here. These two things are equal to each other. This looks nicer, I agree, but we just wanted to illustrate that we're getting this expression when n is k plus 1.
Okay.
So this is like our 2 times n minus 1.
Okay. So did the -1 just come from when you plugged in the n value?
The -1 comes from, I wanted to take this and be able to write it in this form.
Okay.
So this has this form, whereas this, it's not evident that it has this form. So
okay,
we want to show the reader very clearly, I am getting this when I plug n equals k plus 1.
Okay. Thank you.
Yep. And so when you're doing these, you should just do it one way. But if you're kind of curious to compare this side by side, what it would look like if I did it with n's instead of k's. Right, I would get something like this. And it's the same idea. Now we realize n minus 1 and n minus 2 are both smaller than n, so we could use the induction hypothesis. Okay, where I'm plugging n minus 1 and n minus 2 into the induction hypothesis. And then this would give us 4n minus 2 minus 3 times that is minus 6. And then over here, we would get, oh, sorry, there's no 2 here, right? It's 2 times a n minus 1 minus a n 2. So this would give me 4n minus 4 minus 5. And then when we simplify that, oops. Get 2n minus 5, sorry. And when we simplify that, we would get the 2n minus 1. And the reason why this is nice, using the n's, it's a lot easier to match up that we actually showed what we want to show. Because we usually write what we want to show in terms of n. And so if you do the proof in terms of n, it might be a little bit clearer than maybe dealing with something like this. But that's for, we all have different preferences, so I'll let you decide. But at the end of the day, we're doing the same thing. They should look very similar.
Thank you. That made more sense the other way.
Yeah, so I like the way with n. I felt some pushback that people like the k plus 1, so I switched to k plus 1, but I do think it's good to see both ways so that you can decide yourself which way you like. But one thing that is important here to point out, different from the other problems, is that this does require 2 dominoes to knock over the next one. So we require the 2 previous ones, and that's why we need to assume this for all values of k. So this is what the textbook calls strong mathematical induction. So they talk about like weak induction in 10.1, and then they introduce strong induction in 10.2. I think we should just do strong induction always, and that's going to work for the strong case and the weak case. So we don't have to worry about that. Okay, any other questions about this example? Okay, then let's take a look at the next one, problem 4. And this is doing a proof for an inequality. I think we've mostly been doing equality, so it's nice to see some proof with an inequality. So I'm gonna try and just, okay, we've got our typical, we're gonna prove this using induction. And I don't think there's too much confusion on what to do with the base case, but just be sure that it might be clearer to the reader if you just check the left side, you check the right side, and then show, in this case, the left side, it's equal, but in this case, the left side is greater than or equal to the right, so the base case holds. So we've got equality in that case. Okay, and then we've got our induction hypothesis below. We're going to assume that for integers bigger than or equal to 1, less than some integer n, this works for 2k factorial greater than equal to 2k. And then we want to show that this is going to work for n larger than k. Okay, so I'm going to do this one just leaving n alone, leaving it as n. Instead of doing the k plus 1, if you want to do the k plus 1, that's going to work just the same way. So let's consider some integer n, which is bigger than our inductive assumption, k. I have a delay here. There it is. Okay. Okay, so if I deal with the nth case, then what I want to look at is this thing. And again, what the note is up top is that we're not looking at 2n factorial, but 2 times n factorial. And so that's what this means. So we've got the 2 times n factorial. Okay, and again, our goal here, and that's maybe what's nice about using the n's, it's a little bit easier to identify what our goal is. We want to get that this is going to be greater than or equal to 2 to the n. If you're doing the k plus 1, then you'd want to show 2 times k plus 1 factorial is bigger than or equal to 2 to the k plus 1. And so now let me just rearrange these terms. Let me pull the n out here and put the 2 inside of here, like that. And what can I do with this now?
That can be substituted in for our k.
Yeah, so n minus 1 is less than n. So I'm allowed to use this inductive hypothesis because, again, if k is n minus 1, then we're in the range of things we've assumed in the inductive hypothesis. So by the induction hypothesis here, I've got that this is going to be less than or equal to n times 2 to the n minus 1. Since I know 2 times n minus 1 factorial is greater than, oh, I have the wrong direction here, sorry. I know that 2 times n minus 1 factorial is going to be greater than 2 to the n minus 1. That's our induction hypothesis. But I want to get 2 to the n. So what do we know about n in this case?
Well, rules of exponent means that, no, wait. It would have to be another 2 to...
Yeah, so we would need another 2 here. And the question is, why can I do that?
because it's an inequality, you can add things unequally?
So I can do things unequally, right? So really what we're saying is, why is this thing bigger than or equal to this thing over here? Why, when I plug 2 in for n, do I know this is going to be smaller than this? What do we know about the values that n could be? Could n be 1, for example? No, right? Because over here, we say n has to be strictly bigger than 1. So k is greater than or equal to 1, but n is bigger than k. So this means the smallest that n could possibly be in this case is 2, right? So we're considering cases for n is 2, 3, 4, 5, and 6, and so on. So over here, I know that for in the induction step, we're thinking about values of n that are bigger than or equal to 2. So if I set n to its smallest possible value, 2, I know that at worst, this is going to be equal to this when n is 2. And when n is bigger than 2, this is going to be smaller than what we have up here. And that gives me my 2 to the n. So we haven't done something like this in these induction steps because we haven't had inequalities here. But when you're working with inequalities, what I really want to do, I mean, as long as I keep coming up with things that are smaller than or equal to the previous line, we're going to be okay. So I would be allowed to substitute different things in for here. And what I chose to substitute in for n was its minimum possible value. Okay, and now that we've shown, smaller dominoes knock over the bigger dominoes, we've got it. Okay, any questions? Right, it sounds great when someone's doing proofs the right way. That's just why I want you guys to get some practice. It's very different hearing someone kind of narrate how it goes and then trying to do it yourself. So I definitely want to make sure you've got some time to practice it and see where you might be getting stuck if you're having some trouble. Okay, great. So let's think about number 5. I don't think we've gotten into any modular arithmetic yet. So this is a good place for that. So modular arithmetic, this comes up in a field of mathematics, lots of different fields, but number theory would be one very common place where this comes up. And so if you haven't seen this notation before, A is equal to B mod n, what this really means is it's telling you what is the remainder if you divide A by n, essentially. So for example, if I wanted to calculate like something like this, and I wanted to know what is 20 mod 3, then you can think about, well, 20 is equal to 3 times 6 plus 2. So when I divide 20 by 3, I get a remainder of 2. So that's one way to think about these. Any questions about that? Okay, so in 5, let me come over here. We're trying to prove that 7 to the nth power is equal to 1 mod 6 for all natural numbers n. And so, yep, the base case, we plug 1 in. The left side, 7 to the first power, gives me 7. And then we could notice that, yes, 7 to the first power, which is 7, is equal to 1 mod 6, right? Since 7, just to do some scratch work, is equal to 6 times 1 plus 1. So that remainder would be what we get when we take 7 mod 6. So great, that checks out for that case. Okay, so now we want to jump into this induction step. Right, any questions so far? Okay, so yeah, so for the induction, we're going to assume that this is true for all integers k bigger than or equal to 1, less than some integer n. And then we want to show that this is going to work for values of n bigger than k. Okay, and so I hope, again, that these initial steps are getting very familiar to you, so that we can just kind of focus on the tricky part, which is how do we use the induction hypothesis in red to prove the thing in green? Okay, what do you guys want to do here? You want to leave n? What do you like better? N or you like the k plus 1? You chat it in. I'm happy to do either.
N.
Okay, Victoria votes for n. And we have another vote for n. Okay, cool. That's the way I like doing them. But again, if you like doing the k plus 1 and you've been reading the book, go for it. Same thing. Okay, so let's consider 7 to the n. And again, like the key here is you're trying to, it's almost like some sort of Russian doll type of thing when you've got the thing inside of the thing inside of the thing. So we're trying to kind of see how can we use a smaller case, which we've assumed in the induction hypothesis, to help us prove the nth case. And so over here, we can think about that as 7 times 7 to the n minus 1. And so here's where we can use this induction hypothesis. So we know by the induction hypothesis n minus 1 is less than n, that 7 to the n minus 1 is equal to 1 mod 6. And so if this is equal to 1 mod 6, that means 7 to the n minus 1 is going to equal 6 times m. And then we have this remainder that we would need to add in to add up to 7n minus 1. And sorry, I'll come back to that in a second, but that just comes back to this over here. And so all we're saying is that if something is equal to 2 mod 3, that means I can write it as 3 times some integer plus that remainder. And that's what we're using in our proof. And I just introduced a new thing. And so remember that when I introduce a new notation like m, I should explain what m is, right? Is this a real number? Is it a rational number, etc.? And we're dealing with integers here. And yeah. So let's use this back up here, and we can plug 6m plus 1 in for 7 to the n minus 1 and see what happens. Whoa. So I could write this, for example, as 7 times 6m plus 7, distributing that 7. Almost there. We don't want a remainder of 7. So what can we do with this 7?
Subtract 6 from it?
Well, yeah, I mean, we can't subtract 6 or else I would have to, because I have an equation, right? So I can't kind of do something that's going to change this side and not change this side. So I want to leave this over here. So when I'm doing this algebra, I'm not allowed to like do any operations, but I am allowed to rewrite things in equivalent ways.
Yeah, I guess I meant should have rewrite it to plus 1 plus 6. Yeah,
that's right. So over here, we can write this as 7 times 6m plus 6 plus 1 . So I could write this as 7 times 6 times m plus 1 plus 1. I could just pull the 6m and the 6 together. And so now I've got it in the form of 6 times some integer plus 1. And so that was the goal. We wanted to show that when we divide this thing by 6, we get a remainder of 1. Another word to say that is, I can write this as 6 times some integer plus 1. And that gives us our 7 to the n is equivalent to 1 mod 6. And that gives us the final domino. We know they're all going to fall down. Okay, any questions?
Yeah, I don't get how you went from the 7 times 6 times m plus 1 to the one right after it. Like
how I went from this one to this one?
Yeah.
Yeah, so this is just 7 times 6 times m plus 1. So I'm multiplying 3 numbers, and I can multiply these 3 numbers in any order. So I could take 7 times 6, then n plus 1, or I could take 6 times 7 times n plus 1.
Oh, okay. So you just wanted to switch it so that it, okay, I got you.
Yeah, because I wanted it to be in the form of 6, like we had up here, right? So I wanted it to be of the form of 6 times an integer plus 1. So I wanted that 6 in front was the only reason.
Okay, thank you.
Yep. Okay, so I think it's a good time to get you guys practicing some of these. So let's maybe think about 6, 7, 8, and 9. And we'll create some breakout rooms, and maybe I'll assign a different number. What would you guys prefer? Do you all want to work on the same thing? Maybe that's helpful so that we can kind of talk about things together. Okay, yeah, let's do it that way. So yeah, maybe let's give this one a try in 7. We can come back to 6 later, but let's try one of these, number 7. And if you should happen to wrap up 7, feel free to go on to 8. 8, I'll say, is pretty similar. You might want to think about the factorial problem that we did over here for 8. Yeah, so 7 is definitely a little bit trickier. So I'm gonna split you up so that you've got other people to chat with, and Nat and I will be circulating through as well. Yeah, so when we kind of split up the breakout rooms, we say like Nat takes odd, I take even. So I stopped in with 2 groups, Nat checked in with 2 groups. So, and I didn't check in with Nat yet. So I'm kind of gonna base what I saw in my 2 groups, and the other groups, or Nat, feel free to let me know if something different came up in your discussion. But for here, okay, we're gonna do this by induction, and let's consider the base case. And here we're considering integers that are greater than 1. And so just so we're clear, 1 is not a prime number. It's kind of its own certain thing. So a prime number is something that can be written as only can be written as itself times 1. So n would be the first prime number. If n is equal to 2, then 2 equals 2 is a product of 1 prime number. And so I'm just trying to be a little bit careful by saying I'm going to write 2 as 1 times 2, and that's a product of 2 prime numbers, because again, 1 is not a prime number, but 2 is. So it's fine to write a product that only has 1 thing in there. And okay, so that was some discussion that I saw in the groups, like what happens with 1. Okay, and then let's take a look at the induction hypothesis, or the induction step. And if you're kind of having trouble figuring out what should the induction hypothesis be, how do I state that? You almost always can state this like, okay, let me first start by saying what values am I going to assume this is true? So it's always going to be, let me start from the base case that we had and go up to, but not including n. And then the thing that we're going to assume is the thing that we're trying to prove, that this can be written as a product of primes. And we can't conclude this, we're just assuming this. And what we want to show that integers n bigger than k can be written as a product of primes. And I think somebody asked early in the class, like, is there an advantage? Are there some cases when we might want to use n versus k plus 1? And I said, well, it's hard to say. And I realize that there might be one thing to comment on here, and that is when you're dealing like with an induction process, when this domino knocks over immediately the next one, using the k plus 1 might be handy. When you're dealing with cases where you might have dominoes way earlier that are knocking over this one, that's when the k plus 1 probably is not going to be too helpful. So in this case, it's not going to be this number that's going to knock over the next number. So I'm just going to do this on n being larger than k. And so in the groups, we kind of talked about, we have two cases here, which is if n is prime, then just like the case for 2, it's kind of trivially a product of primes. Okay, if n is not prime, that means we can write n as a product of 2 integers. Okay, and both of those integers have to be less than n bigger than 1, right? Otherwise, it would be prime. And since a is less than n, by the induction hypothesis, that this integer a can be written as a product of primes. And the same for b. Right, and so then that would imply that n could be written as a product of primes, since each of the terms in its product, although they're not prime itself, could be broken down into primes. And that would prove it. Okay, so we've run out of time. I'm sorry, I went 2 minutes over, but I think I went 2 minutes short. So for the week where our bank account is even time-wise. So you've got some homework problems that are due on Monday. I would think, in addition, it would be good to think about some of these problems. On Monday, we're going to move on and talk about equivalence classes. So that's what the reading quiz is going to be on. I think that's the plan. Here's your plan. Yeah. So so definitely give these a practice, and we'll be using induction proofs moving forward. But just keep in mind that we'll be starting something new on Monday. So we didn't get to all these. I'll put up the solutions. I think it would be good to try and practice these, and you can check your work against the solutions. And if you have any questions, I've got office hours tomorrow. But otherwise, yeah, nice work on the proofs, and have a nice weekend. If I don't see you, I'll see you on Monday.